morning, everybody. The topic for my presentation today is software services for experimentation and an open WiMAX base station. The outline of this talk is going to be a brief introduction about the project itself, about the goals of this project, and features that we have implemented so far. The main aspect or the main contribution of this thesis is towards enabling programmability of this WiMAX base station. I'm going to talk about the architecture and the two APIs that we've implemented. One is the slice manager grid service, and the other is the datapath generator. And we're going to have an evaluation and experiments that we've conducted that enable the usage of this infrastructure that we've implemented. One is going to be a video service-based experiment, and another one is an emulation of base station handoff. And I'm going to conclude with future work. So this is an image of the WiMAX base station that has been mounted in WinLab. On our roof, we have this antenna, and this is the indoor unit of the WiMAX base station. The goal of this project is to enable multiple base station operators to be supported at the same time. For this, we need to virtualize the resources of the base station so that we have 4 or 5 users simultaneously using the base station. Another important key feature is to support layer 2 programming so that we make the platform IP independent. Why is this important? This is important to enable implementation of clean state protocols, like it could be the caching forward protocol. So if it is an IP independent platform, then we don't have to worry about the IP stack. And we built an API that exposes significant base station control and programmability. For that, we use the orbit management framework, which provides a grid service. Using that, we hosted web services. And a key feature that would be required for any test bed would be a convenient measurement and data collection framework. For that, we use the orbit measurement library, which is a tried and tested method. The final step in this project would be integrating the WiMAX nodes with the orbit framework. Now I'm going to talk about how we've implemented each of these goals. Abstraction basically provides an illusion of owning the entire base station for each operator who's using the base station. And for that, we use a concept called kernel virtual machine, which is basically a virtualization environment. This work has been published, and there's a reference to this paper in my thesis. It's by Gautam. And isolation has been an isolation mechanism has been implemented to ensure resource usage of one experiment has little impact over another operator. For this mechanism, we have something called the virtual network traffic shaping. This has been implemented by Ranak Daya, whose thesis has been published. And the main aspect of my talk today is how we can enable programmability of this WiMAX base station so that you can provide sufficient degrees of freedom to the experimenter. To talk a little bit about the architecture that we've implemented, like I mentioned earlier, we have a slice manager grid service. I'm going to talk about it in detail in the next slide. And the radio resource manager grid service. In a nutshell, these are user-based APIs that are hosted as web services that enable users to use the WiMAX base station. And this is an internal API that creates an end-to-end path between each experimenter and his clients. I'm going to explain the blocks. So these are the two services we've implemented using the orbit management framework. One is the wimaxvm grid service. So when I say slice, I mean it's a virtual machine that behaves as an independent virtual base station. And this wimaxvm service provides and helps us manage these slices that we provide to each user. And the WiMAX RF service is used for radio resource management and measurement. For example, you can get per client received signal strength measurements. You can get the MCS at the client and throughput. So the grid service the web service can be queried for all these requests. To talk a little bit.
So is that what name is a virtual machine?
No, so this is hosted as a web service to the Orbit portal. So you can just log into the, you can query, so there are, I'm going to show
So
you.
this is somehow for an experimenter who wants to see how all the slices
Yeah.
are working.
Yeah.
Kind of.
He can create a slice and then he can check the, like for example, he can check the receipt signal strength at the clients which he has assigned to a slice. For example, I'm going to explain this. Like we have an experimenter exposed web service. For example, an experimenter comes in and he wants to create a slice for himself. He just logs into the Orbit portal and then creates a slice. And then if you need like 3 or 4 clients for your experiment, you need to add clients to your service. For that, these are the parameters it takes in. It takes in the slice ID and the client MAC address. And then after you are done with your experiment, you destroy your virtual machine. This is to talk a little bit about the data path generator that we've implemented. So if there was a one-to-one mapping, if there's one base station and its respective clients, we don't really require to remap the entire thing. But since we have 4 or 5 virtual machines, 4 or 5 virtual base stations, we need a mapping between the user and its respective clients. So for example, if a slice manager creates a slice and wants to add clients to a service, he says, this is the slice ID and this is the client I want to add to my slice. The data path generator is an element which communicates using TCP sockets to the NEC controller, which has information about the clients that associate with the base station. So when a client comes in range of the base station, it gets a GRE tunnel number and its client ID. That information is given to the data path generator. It aggregates this data and creates an end-to-end path between the slice and its respective clients using the click router. I'm going to talk about how the click router works and what it essentially means. So a click router is used for frame forwarding. So this click router that I'm talking about is a flexible and configurable software router. And the data path generator element, like I said, if this is your virtual base station, packets are forwarded to the bridge. You need some way to forward it to your respective clients that you've added to your slice. So the click router basically enables an end-to-end tunnel. It creates the VLANs and creates this path. So to basically summarize what I explained, so if you want to set up an experiment, you create a slice using the grid service. What that does for us is it creates a virtual machine and it creates the respective VLANs are created. And then when a client actually associates with the base station, the NEC controller basically talks to the data path controller and gives it information about the clients that are registered. So this is the MAC address and this is a GRE tunnel number for that client. So the data path controller knows how many clients are associated with the base station. Now the user says he wants to add a client, add 2 or 3 clients to his experiment. So he gives in the add client command with his slice ID and the MAC address of the client. So the data path controller aggregates this information and updates the virtual mapping table. So basically it creates the VLANs and creates the end-to-end data path. And information is sent to the user that the client has been added to the
So when you create the slice, is there some allocation of radio resources associated with the slice?
No, so when I say create a slice, all it does for us is it creates a virtual machine, which is an independent environment where the user can operate. You can load your software and you can run measurements on that platform. The slice manager doesn't do any kind of resource allocation. That's handled by the radio resource service.
And so who set whatever you call the radio manager here handles that?
Yeah.
So so what happens if like the base station's already kind of overloaded? At what point does the person who created the slice find that out?
No, so the way it works is, so if you have 3 users that are using the base station already, and another user comes in, it just creates the virtual machine for the slice. And then the radio resource allocation is handled by the traffic shaping mechanism, where we decide how much traffic or how much bandwidth to allow to each of the slices. That deals with the isolation and resource allocation.
Okay, but somehow that doesn't exist in this picture.
Because this really talks only about the about how you would set up the experiment and how you would be, yeah. So now to really justify this design and talk about how you could use any of these APIs, we've set up a few experiments that I'm going to be talking about. One is the video service experiment. The goal of this experiment is to illustrate the ease with which an adaptive video rate matching scheme can be implemented using our software service. So for example, video encoding is a common technique that's used to do matching between the client and the offered rate of the client. So encoding a video to match the rate of the client per client basis could be a computationally intense task. So for example, this is an experiment that I conducted. So this is the floor plan of WinLab. There's a WiMAX client that has a video being streamed to it, and I'm walking away from I have a path along which I'm walking, and this green region shows that the received signal strength of the client is really low. You see that the rate. This graph shows the throughput and time. So you see that the rate drops really low, and the video that I'm streaming is a constant bitrate video, a 4 MB video. So we are proposing some kind of a rate matching mechanism where we make use of this information about the rate of the client and match the rate of the client to the video we are streaming. I'm going to talk a little bit about that. So this is what we did. So instead of encoding the video at each client, so we have rate information about each client. So instead of encoding the video to match the rate and sending it, that's a computationally intense task. So what we're doing is we're creating 3 slices using our grid service. And we have 3 videos being streamed, a constant bitrate video of 9 MB, 4 MB, and 1 MB. And we have the radio resource manager grid service, which has information about the rate at each of these clients. So what happens is we check for the rate at each client, and we say if these 3 clients are in a good, if the offered rate is good, then you stream a 9 MB video to them. Instead of re-encoding the video each time and streaming it to each client, we're saying stream it to these set of clients. And then as the client moves to a region where its offered rate is much lower, we stream a medium quality video. For example, okay, I think it's the next slide. So that's the idea behind this. We switch clients from one slice to the other, depending on the rate offered to the client.
So are you multicasting this?
No, we're not multicasting.
So it's 3 separate transmissions of the 9 megabit per second stream.
Because the base station doesn't really let us unicast from each of the slices.
Okay, so what does it mean then? Grouping clients into a single slice. So all those guys are in one slice dedicated to the 9 Mbps, but they're basically 3 separate unicasts in one slice.
Yeah.
Right, and that slice is going to become 2 members when one of those nodes moves to a less good quality region.
So it's there's a switching logic which hands over the client to another slice.
Okay.
That's what the infrastructure, that's the goal of this experiment, to show how you can use the infrastructure. We're saying you can switch the client between slices and stream the right kind of video. So, is that?
Oh, I understand.
Okay. So to actually evaluate the video quality, we need some kind of a metric. For that, we're using an objective metric.
So if you're doing like the slices act as separate base stations, right?
Yeah.
So do you have a handoff protocol? Because effectively, when you switch slices, isn't that then a handoff?
So it's not exactly, it is you're handing off the client to another slice in the sense that like I explained, you have the add client function that we've implemented, right? So we're just saying the client has associated to that particular slice. So it is some kind of a handoff mechanism where traffic is routed. A path is created from that slice to its client.
But within a single base station that's running this virtualization,
Yeah.
there's no re-authentication or anything like that, which is traditionally associated with handover.
No, there is no reassociation. So essentially, there's just one base station. There are 10 clients, right? We are creating the illusion that you have four base stations, four virtual base stations, and we're saying the
But who sees the illusion?
we are creating the path, right? The end-to-end path and segregating traffic.
So I'm saying, when you say, oh, we create the illusion, it's not an illusion to the mobile terminal.
No, not
Because the mobile terminal, you're saying, doesn't see a new base station when it is assigned to the next slice. It sees the same base station.
Yeah, it does.
So who is, suffering from, who is seeing something? Who sees multiple base stations if not the clients?
So the experimenter, right? So if you want to set up an experiment, if two people want to use the base station at the same time, you would need independent environments to set up your, say, you want to run a VXC server or you want to set up a protocol. You need independent environments to do that. So this is what that provides. It provides you two environments where you can
I think you should point out that the purpose of your experiment was to exercise some of the design that you did. For a video experiment of this sort, you could also do it inside a single slice if you wanted to. Right?
Yeah.
But your purpose was to show how you can use the software to move from one slice to another dynamically.
Because it's not really clear why you would want to do this experiment, actually, to me. I mean, if the idea behind virtualization is to create several virtual base stations, you're now forcing base station 1 to only serve 9 Mbps, base station 2 to only serve 4 Mbps. And that's not the way the real world works.
I think it's
So
Yeah, I know, that's what I'm saying, which is from a presentation point of view, you really should convey what Ray was trying to say, which is we're doing this to stress test our software.
okay. Yeah, this basically essentially shows how we can use our infrastructure to implement one of these.
I think you can point out the validity of this scenario is it's also not always trying to create a virtual base station but virtual services, so you can decide where you want your slice to be. But you could have the same base station and independent services. You can go all the way down and sort of have the illusion of multiple base stations. I think this is one example where you have one
I
base
have
station.
an example where I'm actually using the virtual base station scenario where I'm saying why we have this virtual base station concept. But like you mentioned, this is more a usage of how these slices can be used for a service point of view. So basically this, the observation in this experiment is that along the same path that I mentioned, we basically have this is just to prove that if you had a constant bitrate video being streamed, when the client moves to a bad channel region, the quality of the average PSNR, like I mentioned, I don't think I explained this slide. So basically to evaluate our video quality, we are using a metric called PSNR, and Evaluate is a well-known software tool used to evaluate video quality, and it basically measures the average PSNR between the original video and the video at the client end when you receive the video. And in this example, what we've done is we've streamed a constant bitrate video and seen the average PSNR recorded. We see that streaming a constant bitrate video all along and not checking for the channel condition does not.
So what is the x-axis? The bottom axis?
So the y-axis is the modulation and coding scheme
No,
at
no,
that
that's
point.
the,
Or the y-axis,
PSNR is the y-axis. The x-axis is,
the modulation and the coding
You should
scheme.
explain that it corresponds to the movement of your mobile in the previous diagram.
Yeah. So this is the experiment that the graph implies. Basically, you're moving along a particular well-known path, and you're recording the rate at that client for that path. And then this is the constant bitrate video that I've streamed. In this case, it's 4 MB. And now in that graph, I'm measuring the average PSNR corresponding to this video on this path.
But you're,
So
In the next slide.
Go back to that slide. So you should point out that what you're showing there is the change in bitrate over time. And but if the axis is really the time axis and the PSNR is going down.
Yeah. But yeah, so it
so
is.
is that the time axis associated with the movement along that
Yeah.
trajectory?
Yeah, it is that. So it's along that path in this particular time frame. This is how the 9 MB video would behave. Initially, it has a good PSNR, but as the client moves away in that in this region, right, when the quality of when it's in a bad signal region.
So I'm just trying to understand that
Yeah.
graph. Is my office in that graph? That picture? Is that
No,
Karen
so it's
Ray's
along this
office?
path. I'm sure you've seen me walk at least 100
Okay,
times.
well, I'm just trying to get it straight, so just tell us, like,
Okay, so
I see the orbit. the control room.
Yeah, this is the control room. I walk out of the lab, and then this is the main entrance
way
of
over
the
there.
lab, and we're sitting here. So I walk all the way to the end of
This
this
one.
path,
Okay.
this region. Somewhere here in this path, we see that.
Ah, yeah, my office is over there by the, got it, okay. So you didn't draw sort of the main bullpen where everyone sits. It's over, will be over where your text is.
Yeah.
Okay, all right. I
So
understand.
now,
So now where's the channel back?
So when I'm walking along this path, this region,
Yeah.
you see that the received signal strength is really low and the rate drops. So we've specifically chosen this path to show the variation in the rate received.
So then at the far right, when you're walking, you're almost back to where you started, and the channel's pretty good.
So this is the experiment. I walk out, walk
Right.
all the way to the end, and go back.
Right, so this is where it gets
getting
good
better.
again because you're back to where you
Yeah.
started.
Yeah,
Okay.
but yeah.
now,
So now the question, right,
yeah, I think we're both.
somehow so how come the green one didn't go back up?
Because I haven't plotted the other half. That was
So
a
that's
reason.
the
So
thing
there's
that in
been.
presentation you need to correlate because this is kind of a vague axis here with 64 prime. That's
So-
kind of loosely showing the region, but you should plot the time accurately.
So you go from 64
So-
to the 1 to 16 with some other code, with half rate code.
And this is
So she's really down.
the
to
lowest-
lowest point.
lowest point when I reach the other end. And I haven't plotted the way back, the route back to the control room, basically.
So it doesn't hurt to have another plot below that, just the time and RSSI that correlates with that. Because it's hard for people to mentally switch that graph and figure out how much of it applies.
Right, but we should then interpret this as some phi adaptation scheme that, which is not under your control, is choosing to switch from 64 QAM to 16 QAM to QPSK and so on. And you've just associated during this fraction of packets, it was 64 QAM. This fraction of packets, it was 16 QAM.
No, so
Or
when
did
I
you?
no when I walk around with the client, right, it gives me the parameters. It gives me the MCS at the client,
Right.
the rate received at the client.
Mhm.
Those two parameters are marked. So I've timed it, and then I'm walking around, and this is the
But you're timing that related to packet sequence number, right? Not
Yeah.
related to, I mean, you're saying this packet, 101, was transmitted at 64 QAM, and it got a PSNR of 30.5.
yeah. That's how I have a table that matches the two. It's mentioned in the thesis.
Yes, I think you should point out here why your results are interesting for first of all, people today cannot do a cellular video experiment. There are companies formed which are doing only this, trying to match the rate. Now what you're able to do now is show something reasonable or not, explain why this graph is relevant.
Yeah. So, I mean, the reason I have this graph here is to actually imply why I'm what I'm doing. The next step is I come up with a scheme where
Now why don't you just explain the previous one? So explain why the red line is.
okay.
Yeah, I might as well tell us all,
Yeah.
because then I'll ask you, well, what about the blue line? So you explained the green line that
Yeah.
as the
So
channel gets worse, the high bit rate video deteriorates in quality. Is that right?
Yeah, and why
Yeah.
is that?
and that's because the offered rate of this modulation and coding scheme is very low. It corresponds to this rate. So I'm trying to stream a 9 MB video.
So why do you get as high as 25?
PSNR 25 seems pretty good if you're streaming 9 megabit
No, actually
video.
the range is that, right? So the video is, so I'm using a high def video and encoding it to different schemes here, a 9 MB scheme and a 4 MB and a 1 MB.
Right, so there are many questions here. So the 9 megabit per second stream, at the point where you're transmitting it through a radio link that's 3.5 megabits per second, what's happening?
I'm pumping more traffic than it can manage.
Yeah, where is the traffic? Is you're gonna drop packets somewhere?
Yeah, that's what's happening. So it calculates. So average PSNR, what it does is it compares the video received at the time with the actual video.
So why is your video any good? Is my question. If it's a 9 megabit per second video transmitted over 3.5 megabit per second link, well, why do you see anything other than sort of stuttery video garbage?
No, it is stuttery, but it's not. It's you can watch the video. It is not
You
really
should
bad.
mention that what is the rating quality as it correlates to PSNR. So 25 is it really bad, watchable, what is
Okay,
it?
so there's a
25
metric.
is supposed to be broadcast quality, right?
Yeah.
Generally.
So there's a metric called. So the way a video quality is measured is between 20 and 25 is considered to be poor to fair quality video, and when it's between between 20 to 25, that's what I said, right? 20 to 25 is considered to be a poor to fair quality video, and between 25 to 30, the quality of the video is supposed to be good, and anything beyond 30 is a very good quality video. That's the metric.
So why doesn't your video really stink? Your 9 megabit per second video.
It does, right? It goes down to that
But
fair
that's only
quality.
fair to medium. So why is it still watchable? I'm really serious. It's like, why aren't 2/3 of the packets being lost somewhere?
They aren't being lost.
Why is it you lose 2/3 of the packets and still watch it? I mean, is there somebody who's kind of, massaging this in some way, or?
There's a buffering going on, so what you see here is the effect where you're walking, and there's a couple of seconds in which this occurs. The buffering helps you to recover perhaps half and delay.
There is definitely a
So
delay.
the delay is not counted by the PSNR calculator.
Is that what's happening? Say you stayed at that end of the building. What would happen then if you didn't walk back to where the channel was?
So it's a flaky video where it keeps getting stuck, and then you get a better quality video. And
Is your quality metric just looking at like the frames as they're received, and the fact that it gets stuck and waits doesn't count against your quality?
So I'm not sure this is taking delay into picture because so there are 2-3 metrics of how you can evaluate a video. PSNR is one of them, and another way to the simplest way to evaluate the quality of a video is a subjective metric where you're looking at the video and you can tell whether the quality is good or
So
not.
you were looking at the video, so maybe you can answer it.
Yeah,
how
so
did it
to
look?
answer that question, when I was at that very other end, the video quality definitely stank. It wasn't great. So it was a flaky video where I could, it keeps getting cut, but I can actually see the entire video with delay.
Okay.
So, short answer, which actually doesn't seem to be coming out here, is when we do video quality assessment, we miss frames. We just use the most recent thing that we had as
And
a
look at the
surrogate.
quality of that frame.
And that frame
Might be pretty good.
might be
if it's
good enough to
trimmed.
get 20 or 25 PSNR.
I think 20 dB is supposed to be watchable. But she will get down to 20 if she stayed in the bad area. It's just the way these.
So you just walk too fast to see what is that basically.
The other factors, it's also highly video dependent. We have no idea about the level of motion in your video. If your video is going through high frame
What was the video?
motion,
So it was a sample video from one of these.
What kind of?
It was a low to medium motion video. There's no fast movement. So they had categories
Do
where
you have detail? What did it look like? The advertising video?
no, it was a
Natural scene?
natural scene. It was
Natural scenes are easier to code. But so going back, I think you should explain to the group why this result might be interesting to somebody. The fact that red peaked and then blue.
So the actual essence of this is to show how we can use our infrastructure. So I must confess that I'm not an expert on video encoding, so I had to learn.
So that's okay, but
these,
at least what did you learn from this?
So the idea is we have to kind of maintain the PSNR at a constant height. So what could we do to maintain, not a constant height, a watchable rate. So where we are trying to maintain the PSNR in this range, where the PSNR is always at a rate between 25 to 30. So what we propose is when your client is in this region, you take an 9 MB video, and as it moves away or as its channel quality drops, you pick a video that has a better quality. So the observation we made out of this graph was videos with different bit rates peak at different MCS values. We make use of that information to say that this region you're going to stream a 9 MB video, and when it is in this region you're going to pick a 4 MB video instead of streaming a 9 MB video, which does bad. And then as the client moves away and when it's in that corner, you stream a lower bitrate video. That's a
So the picture that is the channel moving to the right, the channels get worse, and that makes sense. But honestly, I don't really understand. If you go to the extreme one of the blue curve, right? Why when the channel is its best possible is the PSNR of the blue the worst, and then when the channel is the worst, the PSNR is the best.
So it's
still the same video, it's just going through a crummier channel, right?
yeah. So it's not just about the channel quality. Also, it's about the bitrate that can be offered, right? So at this point where you're streaming a 1 MB video and the channel quality is good, but the bitrate offered is this, so it matches, and that's the reason you have a better quality video.
So what do you think's happening when you transmit at a higher bit rate? What's the grading quality of the video when you send it faster?
It deteriorates at this point because
No, the blue one, it deteriorates when you send it the highest rate.
Yeah. So what's the?
So the question is, why is sending at the high rate not good for the blue? For the 1150?
Because the rate offered is high, but the channel quality when I checked this might have been bad.
But it was pretty good, right? Because it's the same channel quality as in the green. Isn't it? It's the same trajectory, our channel inside the building doesn't change much.
Yeah, it does depend on interference. Each time a person walks in, the channel quality changes drastically.
Okay, so suppose you just did experiments with the lowest rate, the blue rate,
Yeah,
and you repeated your experiment 20 times.
yeah.
Watched the same video, you walked the same hallway, and then you made the plot. Do you think you would see that same blue curve, or would you see?
I might
Things
see this
very, very
improve a
different.
little,
Uh,
but
Yeah, so I think Roy's question is why is the blue going up? And I think there's a simple answer to that, but let you answer it. Why is it going up as the channel gets lower?
because there's a rate matching that's happening. So at so there's a 1 MB video and it's not dropping too many packets at that point of time. So that's the reason the
But why would it be
PSNR is
dropping more packets
Over
at the
there at the
64
higher rate.
QAM
with the better channel.
with the better channel?
because of the channel quality.
But the channel quality is supposed to be good because you're
Using the higher
you're
rate.
you're using a higher rate and you're also
No, but the higher rate doesn't help you with the blue because she's sending CPR at one anything. So the higher rate, what you're seeing on this side is the intrinsic video quality. And that can also fluctuate. But the rise is due to the fact that packet loss rate is also significant in the others.
So you're saying that the base station is kind of really has a mismatch in the channel rate it chose, the MCS it chose compared to the actual channel quality.
In some cases, I think the blue one is better matched as the thing drops down. One megabit keeps getting through, whereas the others have 30% loss rate. But it's a complicated. The thing is, the video quality itself is not constant over time. So anyway, I think our reason to ask it.
So we have some other
was
thesis here,
not
right?
not to do a video research,
Yeah,
but
yeah.
to do an experiment to show that it works.
So the software works to do this switching. That's
I mean,
really
yeah.
what you care about.
Yeah, the software works. Plus, the idea is to show how you can implement one of these methods. I'm going to show how. So, like I mentioned earlier, we have three slices, and each of them are streaming a constant bitrate video that we mentioned. The radio resource grid service that we've implemented gets the rate at each client, and you can log it into a file. And the switching logic that has been implemented helps you switch the client from one slice to the other. So depending on the rate measured, it decides which slice to associate the client to, as in how to create the end-to-end data path. And I implemented a simple adaptive rate matching mechanism where I poll the rate at the client every second and get the average it over 4 seconds. And so the goal of this was to match the downlink rate at the client with the video rate we decide to stream. And this is the rate at the client that was recorded, and this is the rate we predict. Using this average scheme, we say when the rate is high, you need to stream this particular stream of video, and then when the rate starts dropping, you switch to a 4 MB video. So that's just one scheme, and we've come up with 2 or 3 schemes. And to implement this, you need 4 or 5 lines of code, and you just have to use one of those functions to switch clients between streams. And this is an observation of how the PSNR would behave when you stream just a plain 4 MB video, and when you have that adaptive mechanism where you switch clients between slices and decide what to stream. So we see that the PSNR is maintained at a higher rate when it doesn't drop down to a very low rate. But we must admit that this averaging scheme is not suitable for a fast moving client, as the average time is high in our case, so I'm averaging over 4 seconds. So if the channel is, if the client is moving very quickly, I'm not really making use of that. I'm not giving that consideration because it's over 4 seconds. So maybe if we reduce the averaging period to every 2 seconds, then a fast moving client would also fare well in this scheme. And the next example.
So let's go back to this example though. But so there's a scheme here which somebody else could do a thesis and try to have better schemes for the averaging. But somehow what your thesis is about is how the experimenter implements them. So how does that really happen in terms of?
So in terms of how he would implement it is he would have to pick the add client. So this, right? This is what enables you to actually create the end-to-end data path. So this is a C code which communicates with the slice manager, which is a web service, and the NEC base station controller, which is queried, and it gets information. So it's essential to create that path when you switch slices. If the user decided to switch clients between slices and implement an experiment like this, he should be able to do it on the fly and do it with ease. So that's what this implements. So you can just use that add client command when you want to switch between the slices.
So it's the add client adds a client to one of the virtual base, to one of the slices,
Yeah.
right? So in that experiment with the adaptive
Yeah.
scheme, right? So at the point where you want to do the adaptation, you're essentially reassigning the client to a new slice.
Yeah.
And you do that by doing add a user to this slice, which happens
You
to
use
be a
that in your
user.
code. Yeah, it's just a function
I
that you
think
use.
it's sometimes useful to actually show simple scripts that you use.
I have that.
So if you have it as a backup slide, you
Yeah.
can explain.
I have that for the.
And the code that determines that, oh, we should switch now, right?
Yeah.
Who runs that code? What box?
The experimenter. So if you know that you want to implement a video experiment, you can use this add client command either from your virtual slice or as a grid service or as a.
But someone who gets the measurements of where, like, deciding, okay, now look at the average PSNR average, like, somebody is accumulative, some entity in the experiment is looking at those numbers and making decisions when to switch, right?
Yeah, so that's written by the experimenter as a. So the goal would be here. Say I want to conduct a video experiment and I want to set up an experiment. What infrastructure would I need? So basically, I should be able to set up video servers on that slice. So for that, you have on the virtual machines, you can run independent VLC servers.
Right.
We have that convenience. Yeah. And then once you set that up, you should be able to say, okay, fine, now I decide that I want to switch the video traffic from this slice to another.
Do you make that, is that a pre-scripted thing you do?
It's not
beforehand?
pre-scripted, it happens dynamically.
So somehow you wrote a code though that
Yes.
looks at a measurement that has a, given what I've observed so far, I'm gonna switch to this slice.
So he's asking how do you query MCS?
Where does that code run and who, is that part of?
So the radio, okay. Yeah. So if you were an experimenter,
Yeah.
you would have a slice and you would have your independent virtual machine, right? And then you can query this radio resource manager grid service to get your measurements like the MCS, the PSNR, and all that. This user-based service gives you that
So this runs
freedom.
in the real time of the experiment, it's not an offline. So you get those measurements on a per.
Real time
Like what
basis.
kind of time frame? Like is it milliseconds or seconds?
No, so for example, the radio resource grid service gives you the rate or the MCS of the client per second. So for my experiment, I said I'm querying it every second and averaging it over 4 seconds because it doesn't make sense checking for the rate every second and then switching, right? Because it's a video, and if I'm not moving too fast, I'm walking. So the chance, I mean, for my experiment, I decided
Yeah.
that I'm using it every 4 seconds. But it gives you the rate and the channel quality every second. And this service can be used to switch your clients between slices. The datapath controller basically is the essential. The crux of this would be you should have that freedom to say, okay, fine, I want to switch traffic from one slice to the other.
So a script is essentially a script program.
Is being generated.
No, but it's you as the user where you picture a person there's a script running that receives these measurement numbers, has some control logic, and then changes the context the slice manager to change which slice percentage. Okay.
And I use that in my script.
So, I think Warren and I probably are both experiencing some of the same uncertainty about thesis, the way you're presenting it. Not so much about the work you did, but just the way you're presenting it. Up front, you presented, what my thesis is that we are able to put together a sort of a software collection that can support virtualization of WiMAX basestation and so on to support these experiments. Then you go off into your actual experimental part, and your experiments don't support your thesis. Your experiments are, we did some things with the software that we built, but they're not actually supporting your thesis. I mean, looking at all of them, the natural way you would want to actually support your thesis would be, look, my type of experimenters, they need these type of guarantees. They need to be able to query such and such at a rate of, once every 2 seconds. And now you should show me that, yes, your querying can be done on this at a rate of once every 5 seconds, and thus you meet the criteria of your user. Instead, what happened, if you'll notice the questions that both Rory and I asked, were sort of around what did this mean on your plot, what did PSNR, how are you doing your rate adaptation, because you kind of moved us into thinking that you were actually developing a video thing, which we know you're not, right? So I know you're going to move on to the next example experiment, but think about, as you're telling us about the second sort of experiment, how your software supports this, rather than this is what my experiment was and look at the numbers I got. Because then we want to say, oh, well, your experiment, you're now going to do basestation handoff. We're going to ask you about basestation handoff. When really what you want to do is say, look, basestation handoff's an important problem, and I need to be able to provide this to my user. Look, I can provide this to my user. So as you move on to the next one.
So the idea behind the next experiment would be to not really justify or explain how basestation handoff works, but to actually show if an experimenter would come in and had to come up with, if he wanted to do something like a soft handoff or hard handoff and emulate a basestation handoff situation, how he would use this infrastructure that we built is what I'm going to justify in this slide. So like I mentioned, the goal of this experiment is not to really explain how basestation handoff works, but to illustrate the ease with which a basestation handoff scenario can be emulated using this setup. This is an emulated setup because we have just one single basestation and we don't have multiple basestations to show real handoff. So what we've done is we've divided the range of the basestation into two halves. One is assumed to be a virtual basestation 1, and the other one is the virtual basestation 2. And then we say that when the client moves into this region where its modulation and coding scheme drops to this method, you switch to basestation 2. That's the essential idea of this experimenter. And For the NEC base station, we have something called the rate indicator that's measured at the client, and that ranges between 21 to 15. And I'm going to explain how an experimenter can use this setup to explain his experiment. So, client handoff at the base station is emulated using two slices. One is virtual base station slice 1. I create a slice, and then I create another slice, which is essentially a virtual machine. And then, so the experimenter would set up this base station handoff using a simple programming logic in Ruby, which I've explained how he would actually use this infrastructure. And this is how it's a 4 to 5 line code written in Ruby to illustrate base station handoff. So initially the client associates with the base station, and you have information that the client is associated. You query the radio resource manager grid service to check the rate indicator, and if the rate indicator drops below 18, like we've decided that if it drops below 18, you decide to switch, right? So if the rate indicator drops below 18, then you switch client to base station 2 and you move to listening mode. When I say switch client to base station 2, you use the infrastructure to create an end-to-end path between base station 2 and its respective client. You use the add client function again to do that.
So what's that mean when you listen for requests?
So it has to be in this case, the switching logic, I decided to switch to base station 2. You have to wait for a request from base station 2. When the rate indicator starts improving, you need to switch it back to base station 1, right? So the code, basically the base station 1 switches to listening mode, so it's listening for any queries from base station 2 which says I'm switching the client back to base station 1.
So this is the code. Go back to that picture of the code logic. So that's a piece of code that runs at base station 1. And
Slice 1 and
slice 1, and there's a symmetric piece of code, all the ones and twos exchange that runs at slice 2.
Yeah, and the logic for that is explained here. At VBS1 we implement this rate indicator minus 18, and the switching logic at the other end would be 18 minus RI because it's
right. So then and the next in your little the one more. So at slice 2, it's at rate indicators greater than 18.
you switch it back.
Then you switch to VBS1. So why is the line from no? What should it go up to the arrow before it checks the rate indicator?
Yeah, it should.
Because when you check it,
Yeah.
then, right?
It checks the indicator, and then if it is less than, I should make that change.
So you write these two pieces of code.
Yeah, it's a
And
4-line code
So you
uses-
instantiate the two slices this way,
Yeah.
and then run this experiment, and then you actually have a mobile terminal that.
Yeah, I have the WiMAX client, which, so it's the same experiment essentially again. I have the WiMAX client, I walk around, when the rate indicator drops below that particular level, I see it switch to virtual base
And you
station
get rate indications every second.
every second, yeah. I have
Did you use just the one indication to make the, now we're asking, as the first role, you did a pretty good job of explaining the So did you do some averaging or some, if I get one message below 18, then I automatically switch without thinking about it twice?
no, so I did some hysteresis in my thesis. I did some, so I increased the bin. So I have so essentially there's no improvement in throughput, right? It's one base station, it's an emulated handoff. So throughput keeps dropping constantly, right? Because it's an emulated situation. So to do that, you don't really need to check the throughput every second or every 2 seconds. It doesn't really make a difference because you're trying to see if you can switch that instant without any latency.
So if you Like the purpose of such an experiment might be to verify a protocol that somebody has designed and see how long it takes for that to run in realistic setting, but not to do throughput measurement.
But the important thing to be noted is that this can be ported to a real base station handoff mechanism, because if you really had two base stations, it's not too difficult to just switch between the two base stations. Since we had just one, we've divided the throughput into two.
So going back to Wade's point, I think it's helpful somewhere to have a checklist of features that you implement and say experiment 1, experiment 2, and which of the features were
It's using.
verified by experiment 1, which were verified by experiment 2, and hopefully you have more or less covered all the features, like querying MCS or setting up a path. These are features that you offer.
Could we go to actual switch or the server VPS1? Yeah. So the arrows between VPS1 and VPS2,
Yeah.
are those supposed to represent communications between the slices?
Yes, it's implemented using TCP sockets.
And now in the context of your experiment, does that mean when you say handoff from base station 1 to virtual base station 2, usually there is some, handoff isn't actually done until I get sort of an acknowledgement from the recipient base station. So you have that in your logic.
Yes, I do.
And that is supported by the communication.
Yes, so that's the logic here, right? So you switch to listening mode only when you get an acknowledgement that the client has been handed over to the next slice. And once you're in listening mode and then you get a request saying please switch the client to a different slice, you switch the client to a different slice and send an acknowledgement to the client. So it's using TCP sockets to do that, but it does get an app.
So this is maybe a very advanced question, but could we virtualize the other functions of the base station to do things like, for example, AAA functions and other things where we actually do counting and so on associated with such handoff, or is that?
Sorry, I don't really know what AAA function is. If you could.
One of the A's is authentication.
Counting and authorization.
Yes, I think that kind of function can be
Yeah.
to each slice separately.
Well, no, I was just wondering whether you could have another module out here that I guess that's what this server represents.
If you have
I mean, so the server represents that. We're not really dealing with how packets are received at these two slices, right? They receive multicast packets of the information is received at both the slices. So that's what it essentially
but he's
represents.
talking about if you have more complicated handoff, which includes re-authentication, then somewhere there's a AAA server you can model that whole thing through your experiment.
So you could either use another slice for that, or you could have that as a part of these two slices and synchronize it.
That's what okay.
Yeah. Yeah, so this is a pseudo channel indicator which uses that particular formula that I said. So it calculates the, it checks with the radio resource manager about the rate indicator and subtracts 18 because that's our threshold. The plot to show how when it switches. So when the value drops down to 0, you switch to BPS2. So this API, again, like I mentioned, can be used and ported to a real handoff mechanism without too many changes. And to conclude, the crux of this presentation would be to enable programmability of the open WiMAX base station. So for that, we've built two APIs. One is a slice manager API, and the other is the datapath generator, which creates an end-to-end path, and you can change it on the fly. And the next part is an evaluation and implementation of how you could use these APIs in your experiments. And one is one of the examples was a video service differentiation and a handoff emulation mechanism. And future work would involve building more APIs in the radio resource management grid service. For example, we could have features like per packet client error rate, which we are measuring. So these are useful features for the experimenter. And we haven't really looked at the security aspect of the slice manager grid service. Experimenters should not be able to set or reset each other's virtual base station parameters. And the click router script needs to be the efficiency at which it's. So right now we are restarting the click router each time the configuration changes, and that can be improved by including a separate block for the click router.